Good afternoon, everyone. So today we'll be solving some problems related to week 11 content of control engineering course. So basically in this week, uh, you must have gone through a state space, like introduction of the state space, which is modern control engineering. So this week. So while we are trying to represent a system in a state space, we say that the system can be represented mathematically as x dot equal to f of, that is a function of x and u, y equal to g of x and u. So this is the time invariant state space representation of a system. Now here x is the, you can say it's not a, this is a state vector, u is the input vector and y is the output vector. So here if you see the states of the, or you can say at current time, whatever the behavior of system is, it is characterized by initial state and the input up from that initial state time to up to the current time. So past state values, whatever state value it has, the system has before the initial time is not considered, is not required. Now this is general model or mathematical equation for representing a system. So these are basically internal variables and this is the output that is being observed. Now for linear system, this is time invariant. Okay, so it is not varying with time. Now if we have one extra variable which is time, then it would have been time variant. For linear system, it would be like x dot equal to, it should be linear in this variables, state variables and the input. This is a of x du y equal to ex plus du. So this is what we have seen for linear time invariant system. We have this type of representation. Um, for this, we know this is the dynamic matrix. So basically, it shows how the system states will evolve with time. This matrix. So we'll find this transition matrix, which is e to the power at. This is the state transition matrix. And it is dependent on the dynamics matrix, and this is the input matrix. So this is like this. This is the LTI representation, like a state space representation of LTI system. So in the lecture, we have also gone through why this kind of representation is good. Why, where does this Laplace transform that we have seen transfer function representation fails. So if there is multi-input, multi-output system, there we this type of coupling effect between input and outputs that is difficult to model. Anyway, we model it, but in this modeling approach, with this modeling approach, it is easy. For this representation is good one. Also, when we are talking about internal dynamics of system, basically, when we are saying that suppose there is a pole or zero in right half plane, if there is a pole in right half plane of the system, and we are this is s plus 1, and we are designing a controller s minus 1, and this is s minus 1. Suppose this is the controller we are trying to design. So here, if we see this controller, this plant, this plant has a right half plane pole. And this has to be cancelled out by this zero. Now, due to some perturbation or some external factor, because plant model that we are having, whether it's transfer function model or this state space model, are not accurate one. They are simplified model and approximate models of the system. So this cancellation may not be there, and this can lead to instability of internal signals like this U. So this can lead to unbounded U signal. So in this type of condition, it is better if we have access to state variables or internal state of the system. So in that case also, this state space representation is good to have or good to work with. So we'll do some question related to that. Okay. So this is the first question. Consider the following nonlinear dynamical system. This is a state space representation. So x1 dot is a function of x1 and x2. So we can write this the form that we have seen, that x1 x dot equal to f of xu. Now this is a vector. So here there is no u. So this is kind of autonomous system. Its behavior only depends on initial condition. And there are two states, x1 and x2. So this is 14 x1 minus half x1 square minus x1. X2 dot is equal to 16 x2 minus half x2 square minus x1 x2. Okay. So it is asking, the question is asking how many equilibrium points that system have. So this is the system. This has equilibrium point. So basically equilibrium point means any state like point at which so we say that this, suppose this is the state space and x0 is equilibrium point. If system starts at x0, then it stays at x0. So if initially the system is at x0, then as time tends to infinity, it also remains at x0 only. So that means it is not changing. So x dot will be equal to 0. Okay. We'll try to find this out. So that means for this case, x1 dot should be 0 and x2 dot should be 0. Now this is, if we write this one should be 0. So 14x1 minus 1 by 2 x1 squared minus x1 x2 equal to, let us simplify this. So x1 14 minus half x1 minus x2 is equal to 0. This is first one, and second one is 16x2 minus half x2 squared minus x1 x2, and this is x2 16 minus x1 equal to 0. So now let us equate this. So what can we say about this? Let us say x1 equal to 0. So what does this mean? If x1 equal to 0, so for this 2v0, this whole term, can be anything, fine. But for this term, if x1 equal to 0, to for this whole term to be 0, either x2 should be equal to 0 or x2 should be equal to 32, because this whole term should be 0. So the 16 minus half x2 equal to 0, so x2 equal to 32. Now if we consider x2 is equal to 0, then okay, if this is 0, this could be any value, ultimately this whole thing will be 0, so there's nothing to bother about this. I will see this equation, if x2 is equal to 0, for this whole term to be 0, x1 should be 0 or x1 should be 2 into 14, that is 28. Now these are the case when one of these are 0. So let us see another case, if x1 is not equal to 0 and x2 is also not equal to 0. So in this case, these two are not equal to 0 and these two terms are 0. So that means this one and this one. This term and this term should be equal to 0. So what we have, let us simplify this. We have half x1 plus x2 equal to 40. We have half x2 plus x1 is equal to 16. So we have two unknowns, x1 and x2, and two equations. Okay, so we can solve this, and from there what we find, that x1 is equal to 12 and x2 is equal to 8. Okay, so this we have found out. So what are the equilibrium points? We have x1 equal to 0 and x2 equal to 0. This is 0 and 0. And apart from this, we have x1 equal to 0 and x2 equal to 32. So this is 0, 32. Then we have x2 equal to 0, x1 equal to 28. So this is 28, 0. And last one is 12 and 8. Okay, so how many equilibrium points this system has? This nonlinear system. This is a nonlinear system. This system has 4 equilibrium points. Now we know the equilibrium points. So next question is asking, The number of stable equilibrium points obtained by Jacobi linearization. Okay. So how do we find this Jacobian linearization? So if we have a function f of x, where x is a vector, so f of x1, x2, say xn. Now we have to find Jacobian of this one. So what do we say? We just find this partial differentiation of this will give us gradient. But let us see for a state space, we'll just do this one. Okay. So we have x dot equal to f of x u. These are vectors. Okay, so suppose x bar is equal to x1, x2, say xn. Okay, so we have x1 dot, x2 dot, up to xn dot is equal to f of x comma u, and this is n cross 1 vector. This is also function. And then we have f to x comma u, say up to f of n x comma u. Okay. Now we have to find Jacobian of this one. So what do we get? We just, for this one, we just find partial differentiation. Del x1, del f1 by del x2, del f1 by del xn. Similarly, for f2, we'll just find a partial differentiation with all the variables in this state vector. Del f2 by del xn. So matrix. It goes like this, and last one is del fn by del x1, del fn by del x2, up to del fn by del xn. Okay. And for these equilibrium points, what we do, we find the Jacobian. And for this given Jacobian at that equilibrium point, means evaluated at that equilibrium point, we try to find the eigenvalue of this one. So for that eigenvalue, if it is in left half plane or it's negative, we say that the equilibrium point is stable. So we have, let us find Jacobian. This is with respect to x. And then we have Jacobian with respect to u also. So this will again be del f1 by del u m. Suppose there are m inputs. So similarly, it will proceed like this. F1 by del u m. So this is a n cross m matrix, and this is n cross n matrix. Now for Okay, so for this system, we don't have any input, we just have f of x form. So we find Jacobian with respect to x. With respect to u, it is kind of input vector, but with x, we define the dynamic. So we'll be considered with Jacobian with respect to x, which is the dynamics matrix. So this would be, what was the system? Fourteen x1 minus half of this. So let us see if we can find it roughly here. So we have to find partial differentiation with respect to x1. So this would be 14 minus half x square का differentiation 2x1. So this will be x1 minus x2. And then with respect to x2, it would be minus x1. Again, for this one, we have minus x1. This is minus x2. And then with respect to x2, we have 16 minus x2 minus x1. Okay. So this is 14 minus x1 minus x2 minus x1 minus x2, 16 minus x2 minus x1. So now we'll just replace, like, in analyze this one at different equilibrium points. So at 0 and 0, this would be what? 14, 0, 0, and 16. So if we see eigenvalue of this one, these are just diagonal matrix. So eigenvalue will be 14 and 16. For another equilibrium point, so second equilibrium point was 0, 32. Now if we replace this x1 by 0 and x2 by 32, we get minus 18, 0, minus 32, and minus 16. So for this one, eigenvalues are, we can find out, and that would be minus 18, minus 16. For third equilibrium point, which is 28, 0, again we substitute x1 and x2 as 28, 0, and what we get is minus 14, minus 28, 0, minus 12. So what are the eigenvalue? These diagonal terms. So eigenvalues are minus 14, minus 12. And for last one, which is 12 and 8, we just substitute this 16 minus 8 minus 12 and 4. So we try to find the eigenvalue. What we can do, we can just have this lambda I minus a determinant equal to 0. This is one way, or we'll just not go into detail. We'll just use this command in MATLAB. We have minus 6, minus 12. So we have this matrix, and we use this EIG command to find the eigenvalues. And this gives us minus 14.8 or 4.8. So eigenvalues are minus 15 and 5. Okay. So these are the eigenvalue of the Jacobian matrix. So basically, this x dot equal to f of xu, we have linearized at this point. So we have x dot equal to f of x, which is x dot at f x equilibrium plus since it is in matrix, so we like del f x minus x equilibrium. So we are using this one, and f of x equilibrium, because this is equilibrium point, so this is 0. And therefore, what we get the linearized system is x dot equal to del of f transpose x minus x equilibrium. And this one is the A matrix, which we have found out as Jacobian. Okay, so from here, what we get that for these equilibrium point, here we have like eigenvalue in left half plane. Here also we have eigenvalue which is negative. So for these two equilibrium point, the system is stable, or we can say the equilibrium point is stable. This linearized system is stable, and for the nonlinear system, that equilibrium point is stable. For this equilibrium point, it has one eigenvalue in right half plane. So this is not a stable equilibrium point. Here also, the two eigenvalues are in right half plane. So again, this one is not a stable equilibrium point. So these two equilibrium points are stable, and these two equilibrium points are unstable. So what we get, number of stable equilibrium point is 2, and number of unstable equilibrium point for this system is also 2. Okay. We'll proceed to next question. So it is asking the number of equilibrium point of system described by this dynamics. So this we can see, this is a nonlinear dynamics. The equilibrium point we have to find out. Therefore, x1 dot should be 0 and x2 dot should be 0. Now, if x1 dot is equal to 0, this means x2 is equal to 0 and x1 minus x1 cube is equal to 0. Let us simplify this. This will cause equal to 0. And we can simplify further. 1 minus x1, 1 plus x1 is equal to 0. So this gives x1 equal to 0 or 1 or minus 1. So we have 3 equilibrium points. One is this x2 equal to 0. This x1 0 and x2 is 0. And x2 is always 0. So we just have to give this one minus 1, 0. So there are 3 equilibrium points. Got this. Now, what is the next question? The number of unstable equilibrium points. So, for checking the stability and instability, what we'll do, we'll just linearize this system and find the Jacobian of this one. So let us find the Jacobian for this one. Let us suppose this is f1 and this is f2. So we have to find del f1 by del x1, del f1 by del x2, and then del f2 by del x1, del f2 by del x2. Okay. So for first function, it is x2. So del f by del x1 is 0 and this is 1. Now the second one is x1 minus x1 cube. So this will be 1 minus 3x1 square. And this is 0. So this is the Jacobian. And now we'll evaluate this Jacobian at these equilibrium points. Okay. So Jacobian at 0, 0 would be 0, 1, 1, 0. And this one would be 0, 1, minus 2, 0. And Jacobian at 1, 0 is 0, minus 2, 1, 0. So eigenvalues are minus 1, 1. This is plus minus j root 2. And here eigenvalue is plus minus j root 2. So from here what we see, one of the eigenvalues is in left half plane and another is in right half plane. So one of the eigenvalues is in right half plane. So this is a unstable equilibrium point. So number of unstable equilibrium point is 1. Okay, so we have got the concept of equilibrium point. We have solved question related to that, and we have also analyzed whether that equilibrium point is unstable or stable. Now for this linearized dynamics, or we can say any linear system, LTS system. Now I'll see what is the, how do we find the response of that system, state space representation to given input or initial condition. So this is the system, state space representation. This is a linear system, obviously, and UT is unit step, and it is applied at t equal to 0. System initial condition is 0, 0. Which of following determines the evolution of x2? So what do we have to do? We have the system x dot equal to ax plus bu. Now for this one, what we can say? Let's take Laplace transform. Xs axs plus b. Yes. So we have si minus a xs equal to b us. And this implies xs is equal to si minus a inverse b us. So if this is the output and this is the input, what is the transfer function of this one? Si minus a inverse b, this one. We have to find the response of this one, so we'll just find the transfer function. Now this would be what? This is, since A is a 2 cross 2 matrix, no? So this would be Si minus A. A is 0, 1, minus 0.5, minus 1, inverse, and B is 0, 1. Let us say this is XS. And what is US? US is unit step, so it is 1 by S. So we can find this XS. Now, XS is a two-dimensional vector. So this transfer function should be a matrix with 2 cross 1 dimension. Now let us see. This is S minus 1, 0.5, S plus 1. Inverse 0, 1, and 1 by S. We'll find the inverse of this one. So this would simply be, we can apply A inverse equal to adjoint of A by determinant of A. So determinant of A will be S square plus S plus 0.5. And what would be the adjoint matrix? So this is S plus 1, 1 minus 0.5 and S. This is multiplied by this one. And again, this is multiplied by 1 by S. So what we can say, if we multiply these two, we'll get 1 by S square plus S plus 0.5. And this is S square plus S plus 0.5 multiplied by 1 by S. So this would be 1 by S square plus X plus 0.5 and 1 by S square plus S plus 0.5. So this is the transfer function matrix. And now we have to find the evolution of x2. So this is XS, which is this one. Okay, so this is 1 by S square. If we find x2s, so this will be x plus 0.5. Now we can transform this one. So we'll have S plus 0.5 whole square plus 0.5 whole square. And here for 1, we can write 2 into 0.5. So what do we get? We get a form like omega by S square plus omega square. And this S is shifted by 0.5. So this implies x2t will be what? 2 e to the power minus 0.5t because of this one and sine 0.5t. So this is the response x2t. So this is the answer. Now we have to find the steady state value of x1t. So for x1t, we have found out x1s, which is 1 by s square plus s plus 0.5. Now it is asked to find a steady state value, that is x1 t when limit t tends to infinity. So for this one, we can apply this final value theorem. So this will be equal to limits s tending to 0 s xs. And this would give s was 0.5, and this would be 1 by 0.5, which is 2. So x1 reaches the value 2 at steady state. Okay. So we'll proceed further. Now, this is the state space, and we have to find a transfer function. So for this one, what we can do, we have this x1 dot equal to ax plus bu, y equal to cx. So transfer function we know. This would simply be c si minus a inverse into v. So for this one, you'll try to find the inverse of this matrix si minus a, and multiply and post multiply c and b, and you find the transfer function. This is a calculation thing, so I think you'll be able to do this. The answer that you'll be getting is this one. Obviously, this we are expecting because y is a 1 cross 1 vector or one-dimensional variable, so output should be a rational transfer function. It should not be a matrix. Okay. We'll proceed to next question. So this is the transfer function. Now, for this transfer function, we can have different state space realization. And this state specialization, we consider some standard like controllable canonical form or observable canonical form like this one for different purposes. So here it is saying the controllable canonical state space representation of this system. So it is being asked. Now for this one, what we do, we have this ys by us, which is s plus 6 by s square plus 5s plus 6. Sorry. So what we can see, we can introduce a auxiliary variable. So this is zs and zs by us. So we can say zs by us is equal to 1 by s square plus 5s plus 6, and ys by zs is equal to s plus 6. Okay. So we'll define state variables. Now for this one, we have s square z plus 5sz plus 6z equal to us. And if we see Laplace inverse of this one, so we have z double dot plus 5z dot plus 6z equal to u. So here we can say x1 equal to z, we'll just assume. Then x2 is equal to x1 dot, which is z dot, z test. Okay, so this represent differentiation. This also represent differentiation. So this is a second order differential equation. We are taking two state variables because of that. Okay, so what can we write about this? That x2 dot or x2 dash from here is minus 5 z1 dash, which is x2. minus 6z, z is x1 plus u. And for x1 dash, we know it is x2. So from here, what we know, x1 dash, x2 dash is equal to 0, 1, x1 dot equal to x2, and x2 dot equal to minus 6x1 minus 5x2 plus u. So this is the state equation. And for output, we have ys. Ys is equal to sz plus 6z. And for this one is z dot 6z. And for z dot, we know it is x2. So this is x2 plus 6 x1. So y is simply 6 and 1, and this is x. So what is the state space, a controllable canonical form that we are obtained? 0, 1 minus 6 minus 5, this one. Now for this one, for same system, we'll try to find the observable canonical form. So again, for this one, what we'll do, we have this equation ys yus is equal to s plus 6 s squared plus 5s plus 6 . Okay, so let us cross multiply this one. This will give s square y plus 5sy plus 6y is equal to su plus 6u. This is s square y plus s 5y minus u plus 6y minus 6u is equal to 0. Now what we can write? If we calculate y, this would be minus 5y minus u by s minus 6y minus 6u by s squared. So let us simplify this. This would be 1 by s u minus 5y and then we have 1 by s squared 6u minus 6y. Okay, so we'll consider state variables. So suppose x1 is equal to 1 by s, and this is 6u minus 6y, and x2 is equal to 1 by s u minus 5y. So from here, what do we have? These are x1, x2, and the output y is x2. From these two, what we get is Sx1 is equal to, or we can say Xx2. Let us start the second equation. So this is u minus 5y, where u is same, minus 5y is x2. And then for x1, from suppose this is 1. So from 1 and 2, this is 2. We get 6u minus 6y. And this is 6u minus 6x2. Okay, so this we can write in terms of time domain. So this would be x1 dot and x2 dot will be equal to, x1 dot will be equal to 0 minus 6 x1 x2 plus 6u, and x2 dot will be equal to, we missed something. Okay, so for here this x2 would be equal to 5y plus x1. So we have plus x1, so this would give us x1. So this will be 1 and minus 5. And this is 1. And for y, we have simply x2, so this is 0, 1, and this is x. So we have this equation, state equation and output equation, basically a state space representation in observable canonical form. Okay. Now the question is, under what condition on A and B matrix does this hold? So we have e to the power a plus bt, and we have e to the power at and multiplied by e to the bt. So what would be the expansion of this one if we try to find out? This will be I plus a plus b c plus a plus b square by 2 factorial, and this will be carried out. Similarly, for this one, we'll expand individually for each term. So this will be at plus a square t square by 2 factorial, and like this. And for this one, now what can we just multiply this one? What we get is I plus a plus b plus 2 factorial plus abt square plus b square t square by 2 factorial, and you get extra term. So this has to be equal these two. So this implies at into ebt should be equal to 0. Now what is the difference? We'll see. So this is ba minus ab by 2 factorial a square plus, we'll have some larger term is for a plus bab minus 2a square b minus 2ab square by 3 factorial, and here we have 3 cube and some extra term. So for this to be 0, what should be there? This should be equal to 0. Now so that means this should be there, and this can be 0 when also what is there, that this a plus b is equal to 0. This implies a equal to minus b. So if we keep like replace this a by minus b, we'll get 0 only. So this one is also correct. Now this question, consider this matrix A, which is the state transition matrix with respect to A is e to the power at. And when this is evaluated at 1, this gives x, y, z, w. Okay. So what is the sum of these values that has been asked? So we know the system dynamics matrix. We have to find this state transition matrix. So how we define it? This is simply Laplace inverse of psi minus A inverse. Just try this. What is psi minus A inverse? Let us find psi minus A, then we'll find psi minus B inverse. So this is S minus 1 to S plus 3. And psi minus A inverse is equal to adjoint matrix. So this would be S plus 3 minus 2 1 S transpose by denominator or determinant of this one. So this should be S squared plus 3S plus 2. Okay, so this would be S plus 3 1 minus 2 S divided by S squared plus 3S plus 3. Okay, so we have this one. That is correctly. So this is the matrix. Is there something we missed? Okay. So now this is S plus 3y S squared plus 3S plus 2 1 by S squared plus 3S plus 2 minus 2 by S squared plus 3S plus 2 and then S by S squared plus 3S plus 2. So this is the matrix which is SI minus A inverse. Now we have to take Laplace inverse of this one. what do we get? From there, we can see we can do partial fraction decomposition of these terms. We can have this s plus 2, s plus 3, and corresponding numerator, we can find out what would be the value. So when we do partial fraction, like we'll apply this one and we try to find out what is the Laplace inverse. So we get e to the minus t minus e to the minus 2t, then minus 2 e to the power minus t plus 2 e to the power minus 2t plus 2 e to the power minus 2t. So this is what we have as phi t. Okay, now we have to evaluate phi at t equal to 1. We'll just substitute this one. And then we have so this is phi or state transition matrix evaluated at time equal to 1. Now this is x, y, and w, z. So we just sum these terms. What we get is 2 e to the power minus 2. So this is basically 0.27. Okay. So this is what we have. So for this system, for this state space equation, we have found out what is the value of this state transition matrix or equation of this state transition matrix, and we have found out what is the value of this state transition matrix at time t equal to 1. Okay, so we'll proceed to next question. So this says that there is a LC circuit and there are two inductors L1 and L2. There's a capacitor all have value 1 and V is the input U. Now this is the flux across the inductor phi 1 and phi 2 and charge plus the capacitor is Q. So we have to find what is the state space equation. Now for this one, we have these states, which is because these are state like variables because these are energy storing element. We can consider inductor or capacitor. So this will store energy. So we'll consider these as state, which is Q1, phi1, and phi2. And what is the input? Input is this voltage, which is U. Okay, so we'll just try to write the equation. So what can we say about this one? To try to write the equation for this one. So we know the Kirchhoff's current law. So we'll apply this one. So phi, this one, this one. The first equation that we have is that current through this inductor should be equal to sum of current through the capacitor plus the current through the second inductor, which is phi 2 by L2. This is one equation. And then for second equation, what we can have? We can relate the voltage across the capacitor and current through the inductor, that is L2. So we have d phi 2 by dt, which is equal to 2 by C, which is the voltage across the capacitor. So we have this equation, V बराबर L di by dt, or we can say V बराबर d phi by dt. So we have this V and we have this d phi by dt. And for third equation, we will just apply KVL. So we have this loop, we apply this. We have V minus d phi 1 by dt minus 2 by C is equal to 0. So we have these three equations. Now we have to write state in the state space form. So let us write this. For Q1 dot, what do we have? We have this one, this first one. So this is 0, 1, 5, 1, 5, 2. And this one is 1 by L1 minus 1 by L2. For phi 1 dot and phi 2 dot, then we have to find. So for phi 1 dot, what we have? We have this minus Q1 by C, so minus 1 by C. This is 0, 0 plus U. So this is 0, 1, and this is 0, that is V. And for phi 2, we have Q by C simply, so this is 1 by C, 0, 0. Now we know the value of L1, L2, and C is 1. So we have Q1, phi 1, and phi 2 dot is equal to 0, 1, minus 1, minus 1, 0, 0, 1, 0, 0. And then we have 2, phi 1, phi 2 is 0, 1, 0, 0. So this is the A matrix. This is the B matrix. We have x dot equal to AX plus BU. So we have found this out. Now the next question is the sum of eigenvalues of A. So we'll just see what is the eigenvalue of this one. Just wait. So what matrix we are having? A matrix is 0, 1, minus 1, and then minus 1, 0, 0. Apart from this, we have 1, 0, and 0. So we have to sum the eigenvalues. So if we sum these three, let us sum this one here only because this is plus minus, this will cancel out. Sum of answer. This is 0. So what is the sum of eigenvalues of A? This is simply 0. So eigenvalues of A, sum of eigenvalues of A is equal to 0. And for matrix B, we have found out B is 0, 1, 0. Okay. So this is all. So from this question, we have tried to model a physical system, that is LC circuit using a state space. Now, if we consider the output as Q1, then we can convert this into a transfer function that we have studied, that is C for seesaw system. And if we consider that these three are the outputs, then we can have a matrix transfer function. Okay. So this is the system we were having in state space form, and input is unit state with initial condition this one, and we were trying to find out what is the evolution of x2 and what is the final value of x1 in the next question. So we'll just try to like obviously we have found it theoretically. We found what is our transfer function for this system. This is a single input multi output system. So we try to find it out. Now we'll see if we can achieve the same with simulation also. So let us see if we can do the same. We'll just see the response of this system to unit step. So concept we have learned in this week is basically most of the physical system are non-linear system, and then up to now what we have dealt with is transfer function for linear system. So when we are dealing with non-linear system, what we do, we basically try to linearize the system around some operating point. So in this case, when we are trying to see the stability of the equilibrium point, we try to linearize the system around the equilibrium point of the nonlinear system, and we see whether the equilibrium points are stable or unstable. And then we saw when we are linearizing, we can get this beautiful state space representation of the linear time invariant system, that is x dot equal to ax plus bu. And if there is output, which is this y equal to cx plus du. And we related how the poles of the transfer function is related to eigenvalues of the dynamics matrix. Okay, so we have this state space block. In the system, we is a matrix which is 0, 1, and then minus 0.5 minus 1. B is 0 and 1. C is 2 cross 2 matrix because output is y2 and y1. So I 2. This is identity matrix, you can see here. And D is 0. There is no feed forward. And this is a like two states, so we'll have initial condition which is a two-dimensional vector, and for this case initial state is 0, 0, which is given in the this is zeros, 2, comma 2. Why it is incorrect? What should be the zero matrix? DU. So this should be 2 cross 1. Okay. Fine. We'll just apply the input, which is step. Okay, and we have to see the output, so we'll have a scope. And since from here we have output, if you see C matrix, it is a 2 cross 2 matrix, and output is x1, x2. So first one is x1 and x2, so we just decouple this output. So we'll use demux. Let us apply this directly to, we will have to this fine. Just this, make it out. Oh, sorry. Yes. Just a minute. So you can see the response. This state space one shows the first output, and this second shows the two shows the second output. So this is x1 and x2. Now this x1 is going from 0 because initial condition is 0, and for x2 also initial condition is 0. So if you see, this is evolving, x1 is evolving and going to settling at the final value, which is 2. And this is what we found out while we were solving this question. We tried to, what we did, we found out the transfer function for this one. Okay, this is the transfer function that we found out. And this is the x2 behavior, which is e to the power minus 0.5t sine 0.5t. So this type of response, we can see it is kind of a this type of response. We can plot this also, and let's see if we can verify this one. And for this one, x2, we try to find the steady state value. So this is what we found, that is 2 within final value theorem. So this is what we are seeing. Now for this one, since it may be difficult to visualize this one, so we'll plot this response. So the response is 2 e to the power minus 0.5t. This system we have simulated for time duration, that is 50 seconds. Okay, let me see what question is the same. Yes, yes, you have any doubt? This type of exam, you have done assignments, no? So it will be similar to assignment only. Okay, so we'll just try to plot this response. This is, we take a time vector which is 0 to 50. So this is a time vector. And we have to find the response, which is x equal 2 into e to the power. We have exp minus 0.5 star sine 0.5. Let's see if this works. Well, let's do this then. For equal to 1 is to length of. So this is very crude we are doing this, but it is not working. Let us do this one. We'll just fill the data. We'll add after every iteration. So this is 2 into exp 0.5 star t star sine 0.5. Okay, this will work. This is correct. This is 2 e to the power. Okay, this was minus. We'll just plot this one. Plot t comma out. Okay, it seems I have done something incorrect. Fine. So means basically we can try this command, but I don't know. Okay, from here at least you can understand this is kind of the damped sinusoidal response. So from this plot, also you can see this is kind of overshoot, then we have little oscillations because of this one, and then it is settling to 0. Okay, so the thing is that whatever solution or analysis that we have done in the question through theory, that also we can verify in the simulation to MATLAB. And we have got the same kind of response that we were expecting. Okay, so is there any doubt in questions related to stability of equilibrium points, or we are trying to find Jacobian for a given system, and then for given transfer function, how can we realize different type of state space realizations, or for given any state space realization, how do we find this transfer function form? Okay, so if there is no doubt, then I think we can end this session. Thank you.